Crossing the violent English Channel via an underground tunnel has been one of mankind's greatest engineering dreams.
This dream was fulfilled in 1989, after a massive tunneling and sophisticated railway work. However, this simple tunnel train method has a very big technical issue.
Can you spot it?
To understand it, let's look at an example. After pushing the train for some distance, the boy struggles to push it. The compressed spring...
Similar to the resistance offered by the spring, when a high-speed train passes through a tunnel, the air in front of the train gets compressed.
All right, move the excavator back 5 meters. Copy that, moving now.
But to understand the reality, you have to look at a cross-section of the soil.
What if the tunnel collapses due to the immense pressure from the water?
Also, water could find its way through the fault layers.
After a detailed geological study, the engineers decided to drill through the chalk marl.
These detailed diagrams of the different layers of soil below the seabed were not available before the mid-1950s.
To understand the nature of the seabed, engineers had to drill hundreds of boreholes and extensive geophysical surveys.
Interestingly, Napoleon Bonaparte had conceived a plan to build a tunnel connecting France and England across the English Channel.
The idea was first formally presented to Napoleon in 1802, during a brief period of peace between France and Britain.
A tunnel for horse-drawn carriages, lit by oil lamps.
Unfortunately, the war between Britain and France resumed in 1803, and the project was quickly abandoned.
Now, it's time to introduce a robotic caterpillar, the tunnel boring machine.
You can also notice portholes on the cutter head. Hydraulic pistons ensure that the cutter head is pressed against the ground with high pressure.
The muck will start to fill the mixing chamber. A screw conveyor located here transports the muck away. The TBM starts the assembly of the precast concrete rings. Once the assembly is done, the hydraulic piston... The motion of this machine resembles that of a caterpillar, right? These giant machines could not be transported fully assembled. Instead, they were transported piece by piece and assembled on site.
We need to adjust this segment before the next rotation.
Yes, the schematics show a slight deviation right here.
These large individual parts were assembled at the construction sites at Shakespeare Cliff near Dover in the UK and Sangatte in France.
These launch chambers had to be large enough to accommodate the entire length of the TBM. What's happening inside the launch chamber?
Once fully assembled and thoroughly tested, the TBM was ready to begin its long, slow journey.
The Channel Tunnel project required 3 such tunnels, 2 main tunnels and 1 service tunnel. Please have a look at these cross passages.
For any maintenance work in a main tunnel, service personnel enter through the... As we discussed earlier, the discovery of a consistent chalk layer was a huge relief for the engineers.
The TBMs could easily penetrate through it. But look at the shape of this layer. The TBMs had to precisely pass through the...
If the tunnels met with an offset, the project would have ended in a disaster.
How could the TBMs maintain such a complicated course? Remember, satellite mapping like GPS won't work at such great depths. To achieve this, the engineers first had to create a path under the seabed with known coordinates. The tunnel axes the TBM had to follow strictly.
This required the clever surveying techniques and laser guidance system of the Channel Tunnel. The primary surveying done. On a clear day, you can see England from France. Surveyors initially used traditional triangulation techniques.
However, the distance was too great for highly accurate direct measurement across the water. To bridge the channel with the required accuracy,
The advent of GPS further helped with surface surveying. It also confirmed their surveying measurements.
on this known coordinate plane, the engineers could select a few points to create the initial baseline for the tunnel. Once the surface grid was locked in, it was time to take the surveying under the ocean.
The technique for this task is called shaft plumbing.
Demolitions. Shaft plumbing accurately transferred the surface-level survey coordinates down to the seabed. A specialized surveying instrument
At the bottom of the shaft, there is another plummet that looks perfectly straight up to align with the laser or wires coming down from the surface. Combining these two pieces of information, the engineers established the tunnel axis with many known coordinates on it.
Now, the only question was how to make the TBMs follow this tunnel axis. This is where one of the smartest techniques of the Channel Tunnel project came in.
The computer in the driver's control cabin would immediately inform him about this error, and he could take remedial action.
Even though it was easy to drill chalk marl, the fissures inside this layer were dangerous. A tunnel collapse under heavy...
The solution was to strengthen the soil before starting the drilling. Grouting was the best solution to strengthen the soil. The TBMs were equipped with the capability to drill probe holes forward from the tunnel face. These holes would...
Here's a brain teaser for you. The engineers drilled the service tunnel ahead of the main tunnels. Can you tell how they did the grouting for the main tunnels?
This image illustrates everything. Since the service tunnel was already drilled, with these radial drills, grouting could be easily done for the main tunnel's drilling. By drilling the service tunnel first, the engineers mitigated the risk. This also made the grouting of the main tunnels much easier. When they were 100 meters apart, both machines halted. Only one machine drilled forward. This technique is called soft docking. Operating both TBMs until their last meeting point was obviously not a safe method.
Another issue was the possibility of a misalignment.
The first step in soft docking was drilling a narrow, 5-centimeter diameter probe from the English side to the French side.
This task was successfully completed on October 30th, 1990. This confirmed that the alignments of the tunnels were...
After the probe success, a small pilot tunnel was excavated by hand through the remaining distance.
This allowed the historic handshake moment on December 1st, 1990, when British and French workers met for the first time deep beneath the English Channel.
Finally, the French TBM was carefully driven forward to break through the remaining ground, completing the main service tunnel excavation.
We did it! We finally broke through!
Congratulations, everyone!
If you think this is the final geometry of the Channel Tunnel, you are wrong. In fact, the engineers went for a more
You might have seen these large axial fans at the Shakespeare Cliff of the Channel Tunnel. What are they for? They are for the tunnel's fresh air supply.
Fresh air is supplied to the service tunnel at both ends of the tunnel. The service tunnel is maintained at a higher air pressure than the main tunnels.
A total of 11 TBMs were used for this project, 5 from the French side and 6 from the English side.
Theoretically, 6 TBMs were sufficient for this project. The reason for using 5 extra TBMs was due to the different geological.
For the land tunneling, 3 different TBMs were used on the UK side and 2 on the French side.
Surprisingly, 2 out of the 11 machines committed a complete suicide. What I mean is that intentionally driving them into a rock, and both of them were British TBMs. TBMs cannot move backward. It was a difficult and costly affair to dismantle and transport these machines.
Have you noticed these pipes inside the tunnel? What are they for? The trains generate heat due to air friction.
Let's take a virtual train journey through the Chunnel Tunnel and understand this marvel of engineering in greater detail.
The train enters the Chunnel Tunnel on the French side at Chunnel.
You may feel like the train is traveling straight, but in reality, the train follows a complex path through the chalk marl layer.
You will encounter the first rail crossover after traveling 12 kilometers from the tunnel entrance.
Suppose your train unfortunately encounters a technical problem. Thanks to the 2 crossovers which divide the tunnel into 6 sections, Chunnel tunnel service will still continue. At this point, this specialized maintenance vehicle enters the tunnel.
The robust gate in the service tunnel opens. Reorganization these cross passages, the maintenance personnel can enter the running tunnel.
In case of a fire in the running tunnel, this higher pressure will make sure that smoke and fire won't spread to the service tunnel.
After the repair work, the train resumes its journey. The train exits the Channel Tunnel at Folkestone in Kent, on the English side.
We have worked on the Channel Tunnel project for more than 4 months. If you are impressed with this content, please subscribe.